Chapter 6, Part 2. We are still on the process energy calculations based on energy balance equations. Let me think about the energy flows, about heat and work. Energy transfer by material transfer includes kinetic energy, potential energy plus internal energy. Kinetic energy and potential energy of the flows, and also the materials inside of flows have some internal energy. Let's go to the type 2 energy transfer without material transfer. What kind of things are there? Heat and work. So let me think about the heat. Heat is energy flow due to difference in temperature. I'd like to emphasize this part, difference in temperature between the system and the surroundings. So the driving force of energy flow is the temperature gradient. Of course, in the absence of material flow. So total Q, the heat, is integration of heat flow rate with respect to time. Let me think about the sign of heat value. Positive if heat flows from the surroundings to the system. Of course, negative if heat flows from the system to surroundings. Let's go to the work. Work is flow of mechanical energy. I'd like to emphasize those two words, mechanical energy, due to driving forces other than temperature. So the driving force of heat is temperature gradient, and the driving force of work is the mechanical energy. Like in heat, positive if there is mechanical energy flow from the surroundings to the system. So input indicates plus, output indicates minus, of course. Total work is the integration of workflow with respect to time, of course. And work is split into two types of works. The first one is shaft work, S for shaft, plus flow work, F for flow. The shaft work is the work due to rotating or reciprocating equipment, like a starter or something. Flow work is the work due to pressure, so it could be considered as the PV work. So the flow work rate can be PV input minus PV output. In this PV term, V dot indicates the volumetric flow rate. So we have two types of work, WS, shaft work, W flow work. Actually, shaft work will be considered as an important part of the energy balance equations. Okay, finally, we have got back to the energy balance equation. Actually, in very first slide of this chapter, I have said about the energy balance equation. Accumulation is equal to in minus out plus generation, no generation minus no consumption. Because we are thinking of total energy instead of component energy. So total summation doesn't have the generation or consumption term. This is the differential form of the energy balance equations. System energy dt is equal to input minus output, of course. How about integral equations? The final state minus initial state for the system energy is equal to integrated input minus integrated output. Actually, the same equation. The system energy the system energy consists of three things: kinetic energy, potential energy, plus internal energy. For the chemical processes, this internal energy term is very important thing. However, for some mechanical processes, kinetic and potential energies are important. Let me go to the energy flow. This energy flow is coming with mass transfer. And also, this energy flow have kinetic energy, potential energy, plus internal energy, like for the system energy. And also, the internal energy can be replaced by enthalpy energy. Since enthalpy is equal to internal energy plus PV term, so this equation is going to this one. For the internal energy, here I have written down H minus PV. Let's go forward for getting the final equations. In the previous slide, we didn't consider about the heat and work as the direct electron transfer flow. So Q dot and W dot are energy flows without material balance equation, material transfer terms. So they should be included in the energy balance equation. So I have added this one. Okay, let me go back to the original form. So for the system energy, you have three terms: kinetic, potential, and internal. For the input flow, kinetic, potential, and internal, which is split into enthalpy minus PV. For the output, the same. And then here is the heat, plus here is the work. Work term is divided into shaft work and flow work. Also, flow work can be described by PV work, PV input and PV output with the mass flow rate. This PV term is cancelled by this term, this term, this term, that term. So it means the PV term is merged into enthalpy term. Then in the final equations, you don't need to think about the PV term. So here is the final equation, the same, and you don't have the PV term anymore for input, minus no PV term in output, plus Q plus shaft work. I have said the shaft work is important rather than the flow work because the flow work is merged into enthalpy term. Please remember, you have internal energy for the accumulation term. However, in the input and output flow term, you have enthalpy. So please memorize it. Again, internal energy for accumulation and enthalpy for the input and output flow term. Based on this differential form of energy balance equation, you could derive the integral form of energy balance equation. So this is final state minus initial state. Still we have kinetic, potential, and internal for the accumulation term, which is equal to the in minus out for kinetic, in minus out for potential, and in minus out for enthalpy plus Q plus shaft work. No flow work. This is a very generalized energy balance equations. For mechanical processes, in this case, we could have negligible differences in temperature, pressure, phase, and composition. So, you don't need to think about the enthalpy term. Therefore, for the steady-state continuous flow processes, no accumulation is equal to in minus out plus Q plus W. Then finally, out minus in is equal to Q plus W. In the inside of input term and output term, you cannot find enthalpy because the enthalpy difference is negligible due to the similar temperature, pressure, phase, and composition. This equation is applied to the mechanical processes. So, you will not often use these equations because usually we are going to the chemical processes instead of mechanical processes. Therefore, let's go to the next chemical process energy balance equation for steady-state continuous flow process. We could neglect the kinetic and potential term for the chemical processes. Then enthalpy output minus enthalpy input is equal to Q plus W. This is the most popular equation, which is applicable to the steady-state continuous flow chemical process. I'd like to emphasize chemical process. How about batch? Very simple. Internal energy final minus internal energy initial is equal to Q plus shaft work. There are no flow work there. Right now, we have energy balance equations in our hands. Then it's time to go to process energy calculations by using the energy balance equations. Here is some hint for how to calculate the process energy. If you choose the state of one of the streams as the reference state, then the specific energy of that stream equals 0. It's very important to choose the state of one of the stream as the reference state. If you have an appropriate choice, you could simplify the process energy calculations. Please remember, you should choose by your own way the state of one of the streams as the reference state. For many chemical processes, I'd like to emphasize chemical. Many chemical processes involving changes in temperature, phase, or chemical composition, kinetic and potential energy contributions are negligible compared to enthalpy contributions. So, for the chemical processes, well, in most of chemical processes, you don't need to think about kinetic and potential energy term. So you will focus on the enthalpy flow on the right side of the energy balance equations. Also, even in accumulation term, you will focus on the internal energy. Please neglect the kinetic and potential energy for chemical processes. The effect of pressure on enthalpy is usually much less than the effect of temperature, phase, or composition. A piece of equipment with a shaft like pump, compressor, and so on is a good indication that you need a shaft work term. In many cases, you would neglect the shaft work. However, whenever you look at some pump, compressor, or something like that, then you should think about this shaft work term. Here is the example 6.12. Temperature change with dissolution. Caustic tank safety. Let me try to follow the problem statement. Anaerobic fermentation of sugars produce organic acids such as lactic and acetic acid. These acids reduce the pH of the fermenter to unacceptably low levels unless base is added. So we should add some base like sodium hydroxide. You are in charge of designing a small system to make an aqueous sodium hydroxide solution to be used in a fermenter to maintain pH control. Actually, these statements are useless for solving this problem. This is a kind of background. In your design, solid sodium hydroxide pellets are added to a tank containing 10,000 gram water at a rate of 40 gram per meter. So here is the schematic picture for the situations. We have a big tank, and inside of the tank you have 10,000 gram water. Then I will introduce sodium hydroxide pellet. This is the solid phase. Into this water. The input flux is 40 gram per minute. And here is the agitation. Let me get back to the statement again. At a rate of 40 gram per minute over a 10-minute interval. So for 10 minutes, you will introduce sodium hydroxide pellets into water with mixing, complete mixing. The water in the tank is initially at 50 Celsius degree here, while the sodium hydroxide pellets are initially at 25 Celsius degree. If the tank temperature exceeds 70 Celsius degree at any time, safety regulations require that the tank be insulated to protect workers from possible burns. Will you need to insulate the tank? That is the question. So, as more amount of sodium hydroxide pellets are introduced into water, then the temperature will goes up due to some heat of solution. So we should think about that temperature, and that temperature should not exceed 70 Celsius degree. If there is every possibility of the temperature go up over 70 Celsius degree, we should think about the insulating the tank. This example is about that situation. Okay, so system will be tank, and this tank reactor is considered as a semi-batch process because we have water within the tank, so it looks like batch, but during the mixing, sodium hydroxide pellets are introduced continuously into this water, so semi-batch process. Initially, M system initial is equal to 10,000 gram. Also, we have input stream without output stream, so the value 40 gram per minute. And also here shaft work is given to you 0.2 horsepower. You should convert the horsepower into SI unit in this case. So that value is 8950 joule per minute. The conversion factor, you can find it in the internet. Then let's start with the material balance equation before going to the energy balance equations. This is the integral form of mass balance equation. Final minus initial is equal to the input minus no output. So this is the input. And then for 10-minute mixing, so you will integrate the mass flow rate for input with respect to time from 0 minute to 10 minutes. So this initial value was given and stream variables is given with some time. Then you have 10 400 gram solution will be obtained after 10-minute mixing. Still we are on the example 6.12. Then let's go to the integral energy balance equation. So this is the full version of integral energy balance equations. So final minus initial for the system energy terms, and each energy term has kinetic, potential, internal energy. And then let's go to the right hand side of the equation. Then input minus output for the kinetic, input minus output for the potential. Potential, right? And input minus output for enthalpy plus Q plus shaft work. I have emphasized that in the accumulation term, you will find the internal energy. However, for the flux or input-output rate, then you have used the enthalpy instead of internal energy. Anyway, that is the full version. So let me try to recognize what kind of terms should be neglected. So no output, so we could kill the output term here for the kinetic, for the potential, for the enthalpy. System's velocity and position do not change. It means the final kinetic energy of the system is equal to the initial kinetic energy of the system. Also, potential energy, the same thing. I mean, I have said the for the chemical processes, including mixing, even including mixing, we don't need to think about kinetic energy and potential energy for the accumulation term, for the input-output flux terms. Only important thing is enthalpy term, internal energy term. That's it. So anyway, due to this reason, we could kill K sys final, K sys initial, and also potential of system final, potential of system initial. So we could kill those two terms. It's totally 4 terms. Let's go to the green one. Reference state. It's time to fix the reference state. So in this case, we have chosen this stream as the reference state because this is only one the stream, right? We have no choice. So what is the state? Solid of sodium hydroxide and 25 Celsius degree, of course, or might be 1 atmospheric pressure. That is the reference state. So enthalpy term here is going to 0. Then one more thing, neglect potential and kinetic energy flow for mixing. So you could kill this one and this one. So after removing many terms, then we are going to this equation. That is to say, internal energy change in system is equal to Q plus WS. Then let's go to the next step. So here is the worst case scenario. Maybe the temperature will goes up over 70 Celsius degree. So we need to insulate the tank. It means Q flux, I mean heat flux, should be 0. This is the worst case scenario assumed here. So for this case, Q is 0, then the difference of internal energy of system is just going to the shaft work. That's it. And shaft work was given, like shaft work flow was given, actually rate was given. So for 10 minutes, then it is going to this value. So what we have, the difference of internal energy in the system is some value, which is the 89.5 kilojoule. From the previous slide, we have obtained this equation. Again, final state minus initial state for the internal energy of the system is equal to the shaft work. The value of shaft work was given to you, which is the 90 kilojoule. Then, what is the temperature after 10-minute mixing? That is the target question, the final question. So, we should find the final temperature involved in this term, the internal energy of the system at the final state. Let me try to describe the internal energy with the other terms, temperature terms, and some calculated values. Each internal energy should be calculated with respect to the reference state. So internal energy system final state minus each reference state minus system initial minus reference state is equal to the shaft work. You know, this U reference is cancelled here and there, so it is going back to the original equations. In this case, reference state is pure liquid water and pure solid sodium hydroxide at 25 Celsius degree and 1 atm. This reference state is the same as the stream reference, so we have considered the input enthalpy as 0 because the sodium hydroxide, solid sodium hydroxide at 25 Celsius degree and 1 atm was the reference state. So this reference state is the same as the stream reference state. However, this reference state could be different from the stream reference state because U reference, I mean reference state of internal energy, is finally removed in this equation. So you could select another reference for this calculation about the internal energy. Anyway, usually and practically we have used the same reference state. Then let's go to the calculation. First, I'd like to calculate this term, the internal energy difference between the initial state and reference state. That is to say, at time equal to t0 while 0, we have 1000 gram liquid water at 50 Celsius degree and 1 atm before introducing the sodium hydroxide into the water. Temperature deviates from the reference state. Right now we are on the 50 Celsius degree, but the reference state should be 25 Celsius degree. So only one step pathway is enough because only temperature is variable. So here the initial state of the system minus reference state for the internal energy is equal to each corresponding specific one. Specific initial state, specific reference state with the mass inside of the system. That is the 10,000 gram. And internal energy can be described by the product of constant volume heat capacity with the temperature difference. So like that. And T0 for the initial state minus reference state temperature. So 50 Celsius degree minus 25 Celsius degree with the heat capacity. This heat capacity comes from the data given to you, like that. Also, here we have two different heat capacity. The first one is for water. The second one is for the mixture between the water and sodium hydroxide. Of course, in this initial state case, you should use the heat capacity of water, because we are thinking about the 10,000 gram liquid water. Okay, so that value is 1050 kilojoule. This value is about the second term on the left hand side of the equation. Then let's go to the first term on the left hand side of the equation. At time equal to TF, final time, or 10 minutes, then 400 gram sodium hydroxide in 10,000 gram water at unknown temperature and 1 atm. What was the reference state? Pure liquid or pure solid sodium hydroxide at 25 Celsius degree. In this case, temperature is not the 25 Celsius degree. Also, composition is not the pure one. 400 gram sodium hydroxide in 10,000 gram water. That is the composition. So, both temperature and composition differ from the reference state. So, we could construct two-step pathway. The first one is the composition and the second one is temperature. Here's the two-step. The first step is for the composition. Dissolve 400 gram sodium hydroxide in this gram water at 25 Celsius degree and 1 atm. This is the reference state, but composition becomes different. So I have said dissolution of sodium hydroxide in water. What is this process? This is the solubilization process. Well, so in this case, we need to use the enthalpy of the solution. So here is the enthalpy of solution at the reference state. Okay, right now, after the first step, we have the mixture, and but the temperature is 25 Celsius degree. So I'd like to increase the temperature from 25 Celsius degree to an unknown temperature. Therefore, for the internal energy of the system at the final state minus reference state is equal to the first step, composition change. That is the enthalpy of solution with the amount of the mixture. So the amount of sodium hydroxide, because the unit of enthalpy of solution, this enthalpy of solution is joule per gram sodium hydroxide. So the mass should be pure sodium hydroxide. So 400 gram sodium hydroxide with the value of the enthalpy of solution. Here, this one. Plus, let's go to the second step, which is relevant to the temperature difference. Also with the mixture, solution mass. So 400 gram, we have obtained this value from the mass balance equation in the previous slide. With CV, the constant volume heat capacity for the mixture, sodium hydroxide water mixtures. So the second one should be used. And Tf minus 25 Celsius degree. Then finally you could obtain this equation. So this one is for the first term on the left side of the equation, and this is the second term is equal to some value. So like that, and then the first one, then the second one is constant. Then from this equation you could calculate the temperature, which is 62 Celsius degree. Fortunately, even if we have insulated the system, the temperature goes up to 62 Celsius degree, which is less than 70 Celsius degree. That is the safety guideline. So we are enough. So we don't need to insulate the tank for the mixture of sodium hydroxide with water. Example 6.13. Simultaneous energy and material balances. Mel and Dan, the French, Mel and Dan's lemonade stand. This example is very interesting example, even if the statement is really long. Mel and Dan run a lemonade stand. They've noticed that some customers like their lemonade barely cool, not very cool, just barely cool, while others prefer their drinks ice cold, really cool. Always looking for a new way to please their customers, Mel comes up with the brilliant idea of lemonade to order. It means customized lemonade. Mel says he will ask customers for their temperature preference: cool, cold, icy. Cool indicates 60 Fahrenheit, cold 45, icy 35. And then fine-tune the lemonade temperature by adding just the right number of ice cubes to the cup on the spot. Then wonders how Mel can know how many ice cubes to add. But Mel claims to have come up with a simple mathematical formula that calculates the number of ice cubes to add, given the size of the lemonade. The statement means the Mel and Dance provide 3 different sizes of cups: 8 ounces, 12 ounces, or 16 ounces, and the desired temperature: 60, 45, 35 Fahrenheit. The lemonade at Mel and Dance before adding the ice cubes is the same as the air temperature, room temperature, which tends to be about 85 Fahrenheit. The ice cubes are 1 cubic inch in volume and are kept just below their freezing point temperature, around 0 Celsius degree. The lemonade is sold to the customer in insulated cup, so Q heat is equal to 0. Always quality conscious, Mel refuses to sell the customer any cup whose contents are not thermally equilibrated. It means the lemonade, inside of the lemonade, the ice cubes and the liquid lemonade is always equilibrated in terms of temperature. Then find the following notes scribbled on a napkin. Some standard enthalpy of melting of ice is 330 joule per gram, which approximates the internal energy term. Of course, solid, H is equal to U. Also, the constant pressure capacity of water is similarly equal to the constant volume of heat capacity of water, is this value. The other thing is density of water, 1 gram cubic centimeter, as you know, or in other units you would have different values, something like that. So Mel won't divulge his secret formula, expose his secret formula. Can you figure it out? So let's try to find the Mel's equation to expect the number of the ice cubes to adjust the temperature depending on the volume of the lemonade. So this is the system. We will try to expect the state of the system after the addition of the ice. That is our target. And system contents inside of the cup. So this process is considered as the semi-batch process. In the cup we have something here. There is input stream. There are no output stream. We should start with material balance equations. This is the integral form of total material balance equations for lemonade. So final minus initial, that is the accumulation term, is equal to input, integrated input, minus no output. So how about the initial mass of the system? So we know the volume of cup after your customer is saying by the mass is calculated from volume by density. So let me assume that the water density is the lemonade density. So we could use the water density. Then this term can be described by the volume of cup. The other thing, input stream. So this one, I mean the mass flow rate as the input, and then this value should be integrated. It means total mass of ice added to the cup. It means the number of ice cubes with the mass of each ice cubes. So we know the value about the m ice, the mass of the each cube. Then we could say like that. So this one, final mass is equal to cup of volume plus number of cube. Then it's time to go to the energy balance equations. We are on the semi-batch. So for the accumulation term, we have final minus initial, and on the left side of this equation, you could find the input term. So internal energy of system final minus initial is equal to integrated the enthalpy with the mass flux. Let me think about the Q and WS term, plus Q plus WS. So cup is insulated, Q is 0, no mechanical equipment, WS, shaft work is 0. So this is the energy balance equations. And then this equation is going like that, specific energy with mass flow rate, and then also this M in, input mass, can be described by the number of ice cubes with the mass of each ice cube. Then this is the specific enthalpy of ice in. Okay, reference state in this case is pure liquid water at its melting temperature of 32 Fahrenheit. It means 0 Celsius degree and 1 atm. The behind the reference state, we have some assumption that the lemonade is modeled as the pure water. Okay, then let me calculate about the difference of the internal energy of the system. So the first one is about this one, initial one. Initial one, or the initial internal energy minus reference internal energy is equal to, as you know, constant volume heat capacity with the temperature difference. So this value comes from the given value like that, and 85 Fahrenheit is the initial situation, and minus reference, then we could calculate it. And then let's go to the final, well, at the end one. So we have three different choices about the temperature. Let me say TF. F means final. So let me have the variable temperature. It means the final minus reference state of the internal energy is equal to CV, the same thing, TF minus reference. So we have this one. So, and then it's time to go to the right hand side of the equation. Energy introduced to system with ice. So it means ice minus reference is equal to ice minus liquid at melting point. This is the reference state, right? That is the liquid. It means, ice minus liquid means phase change from liquid to solid. Or I could say minus phase change from solid to liquid. So, input stream, ice input stream, specific input stream, could be described by the standard enthalpy of melting of ice. So this value was given from the statement, so minus 330 joule per gram. Okay. Then let's put those expression into these equations. So this one, no, where is that? Okay, so this one comes from here, and 1 to 2 comes from here, and from the mass balance equations we know the value about the M system final, right? Total mass of the system at the final state, and also the initial state, with the M ice is going to 16.4. So finally, by reshuffling these equations, we could obtain the number of ice cubes, which is the function of temperature and the volume of cup. So for example, if you want to here, so if your customer want to have the cold lemonade, then you should put the 45 the Fahrenheit into TF, and also your customer is saying about the size of the cup, then you should the value into the V cup. Then finally you could calculate the number of ice cubes. Then after equilibration you could obtain the desired temperature depending on the size of cup. Example 6.14, energy balance with equilibrium flash, separation of hexane and heptane. Can you remember this example? You have found the same situation in the example 5.16 of some separation. Okay, so a liquid mixture of 40 hexane, 60 mole percent heptane. Okay, let me go to the schematic diagram for this situation. Here's a flash drum, and a mixture of 40 mole percent for hexane and the 60 mole percent of heptane is introduced flash drum. Here is the feed stream. Also, here is the temperature and pressure for the feed stream. Flash drum, we will heat the mixture at 111 Celsius degree. Then the liquid is split into vapor and liquid. So let me check the characteristics of the vapor phase. 111 Celsius degree, the same pressure with the feed stream, and this is the flow rate of vapor phase and composition. Of course, the more lighter compound hexane is dominant in the top stream. Let's go to the bottom stream. This is the total flow rate for this bottom stream and the composition. Of course, in this case, the heptane is dominant, and the temperature and pressure are the same as the top stream. That is the situation. And question is the Q, which is going to the flash drum, should be calculated. Okay, so mass balance equation is not used because already the mass equation calculation is done. So we know every values about the composition and the stream rate. So let's directly go to the energy balance equation. Open system with heat but no shaft work, right? Steady state, no change in system energy, no accumulation term, and kinetic and potential energy are negligible because it is the chemical processes which is the separator. Reference state, we will take this temperature and pressure as the reference pressure and temperature. Also, pure hexane and heptane in liquid phase as the reference state. Then energy balance equation is no accumulation is equal to in minus out. Inside of in, you cannot find the kinetic and potential. Inside the output, you cannot find kinetic and potential. Only thing you can find is enthalpy term. So feed stream enthalpy minus vapor enthalpy on the top stream and liquid enthalpy for the bottom output stream, plus heat plus no work. So finally vapor plus liquid minus feed is equal to heat. So we will try to calculate heat. Okay, the same equation is here, which is coming from the previous slide. And again, I'd like to remind you about the reference state. Pure hexane and heptane in liquid phase at 25 Celsius degree and 1520 millimilli Hg. Let me start with the feed stream. Of course, it is going to 0. Okay, so what was the reference one? Hexane, heptane, but they are pure. And the enthalpy of the enthalpy of mixing of hexane and heptane is 0 because they look similar to each other. So the enthalpy of feed is going to the enthalpy of reference without any mixing enthalpy, so which is going to 0. The third term is 0. And let's go to the second term. This is liquid phase, and reference phase is liquid phase, so you don't need to think about the phase change. Only, okay, so let me read it. Liquid stream leaving the flash drum is at the same pressure and liquid phase as the reference state. So pressure and phase is not changing, but the temperature is different from the reference temperature. So we will use the CPDT equations. I mean CP with the temperature difference. So again, let's go back. So this one, HL, specific enthalpy of liquid, is the heat capacity of the hexane and the heat capacity of heptane, with the composition, hexane composition and heptane composition. That is the averaged the heat capacity with temperature difference. In this case, 25 Celsius degree reference state, 25 Celsius degree going to 111 Celsius degree. Then we could calculate the value. How about vapor? It is a little bit complicated than others. Let me construct pathway from reference state to vapor state. The temperature is different from the reference. 111 Celsius degree for this bottom stream output, but the reference is 25 Celsius degree. So you should increase the temperature. The other thing, the phase. This is the vapor phase. However, our reference phase is liquid. And yeah, that's it. So we have two difference there, temperature and phase. So let me do it. First step, increase temperature of components from 25 Celsius degree up to the boiling point, because at the boiling point the phase change happens, so you should increase the temperature up to the boiling point before the phase change. Of course, we didn't reach yet 111 Celsius degree because the boiling point is this one. This one. Boiling point is lower than the 111 Celsius degree. Okay, so still we are in liquid phase, and then change phases from liquid to vapor at boiling point and the same pressure. We don't need to think about the pressure because the pressure is the same as the pressure of reference state. So anyway, we experience some phase change at boiling point, and then we should go to the target temperature 111 Celsius degree. Increase temperature of components from boiling point to 111 Celsius degree at the same pressure and in vapor phase. Right now, vapor phase. In the first step, we are still below the boiling point, so the temperature is increasing under the liquid phase. However, after phase change, the temperature increase happens in vapor phase. Okay, so we did the 3 steps for each compound, and then as the step 4, we will mix those components. Let's do it. Enthalpy of hexane in vapor for this one is equal to temperature equal to the first step, temperature increase like 25 Celsius degree reference temperature to 69 Celsius degree. 69 Celsius degree is the temperature, boiling temperature of hexane with heat capacity. Then it's time for phase change. So this is the evaporation, the enthalpy. Then right now our the hexane is in vapor phase. Then it's time to increase the temperature from the boiling point to the target temperature 111 with the heat capacity. Then you could calculate it for the hexane. The other thing, heptane, the same way, some value. So finally, the mixture of hexane and heptane in terms of heat capacity of vapor phase is equal to the composition of hexane with the enthalpy of pure hexane value. So this one plus the composition of heptane and enthalpy of heptane. Then this weighted average is going to the enthalpy of vapor phase. Then let me put it there in the very first equation on this slide. So vapor plus liquid minus feed is going to the heat. So finally you could calculate the heat. Heat has a plus sign. It means we should the heat the flash drum for separation. Example 6.15, energy balance with chemical reaction. Here in this example we will involve the chemical reactions in this process. So liquid sulfur, okay, here's the situation. Here is a burner and liquid sulfur is introduced into the burner. At the same time oxygen gas is introduced into burner. So inside the burner we have this reaction. The sulfur plus oxygen is going to SO2. Then in the output stream you could find the sulfur dioxide gas. The pressure is all 1 atm and the temperature for liquid sulfur is 130 Celsius degree and oxygen gas at 25 Celsius degree. The question is, what is the temperature of sulfur dioxide gas? This reaction is exothermic, so when the liquid sulfur is oxidized by oxygen gas, then we could obtain the thermal gain resulting in the temperature increase. So we'd like to expect the temperature developed inside the burner, so finally found in the output stream. There are some data, and then let me try to calculate it. The first one is about the mass balance equations, or the values of each stream. Choose a basis. Okay, so there are no any information about the molar flow rate, so we should define a basis. For example, in the first input stream, the flow rate of sulfur is 1 gram mole per second, and there is some assumption there. The feed ratio between the sulfur and oxygen was stoichiometric, and also they are completely reacted to each other. Finally, all of S and O2 is going to the SO2 in gas phase. So we have 1 gram mole per second S. It means 1 gram mole per second oxygen. It means we have 1 gram mole per second for sulfur dioxide gas. This is a kind of mass balance equations. Then it's time to go to the energy balance equations here. This burner is operating on steady state continuous flow systems, so no accumulation. Also, it is a kind of chemical process, not the mechanical process, so you couldn't neglect all kinetic term and potential term. Okay, then the Q is 0. No comments about that in the problem statement. Also no shaft work about that. So resultantly, enthalpy out is equal to enthalpy in. That is to say, SO2 out, O2 in, sulfur in. So we could use this kind of the energy balance equations. Before going to the calculation, we should define the reference state. Here, this stream is used for the reference state. 25 Celsius, 1 atm in their normal state like oxygen gas, or in normal gas, sulfur solid. In this reference state, the sulfur is solid. So, sulfur solid and oxygen gas. That is the reference state. And then let me start with the first term on the right side of these equations. So oxygen input, I have said I have taken this state as the reference state, so this is going to 0. The second term on the right side, sulfur feed, liquid sulfur. So let me check it. Liquid sulfur is at 130 Celsius degree. However, reference temperature was 25 Celsius degree. So you should think about temperature increase. Also, one more thing. In the reference state, sulfur is solid. However, in the first stream, we have a liquid rather than the solid. So we should think about the phase change. Then, in any cases, we should go to the 130 Celsius degree from 25 Celsius degree. We could think about the 3 steps for the calculation pathway. For the first stream or second term of the equation, energy balance equations. So let me increase the temperature of sulfur from reference temperature to its boiling point. Okay, still we are on the solid phase of sulfur. And then at the boiling point, we should change the phase from solid to liquid. And then from the boiling point to the target point, we should increase the temperature. In the final state, of course, the phase of sulfur is liquid. Then follow those steps. The first one, temperature increase from reference state to boiling point, and this is the heat capacity of a solid. It should be. And then it's time for phase change, so melting from solid to liquid. Plus, we should increase more temperature from boiling point to the target temperature 130 Celsius degree with the heat capacity of liquid phase. And then summation of things, we have the value for the second term on the right side of the energy balance equations. And then let's go to the left one. What is that? That is the product enthalpy in the upstream. We don't know the temperature, and this temperature is the purpose of our calculation. Calculate this one, enthalpy of SO2 out at 1 atm. Everything is 1 atm. However, unknown temperature, so we'll try to calculate that unknown temperature. So construct a path from the reference state to the actual state of the exiting stream. So in the first case, let me react sulfur and oxygen at 25 Celsius degree and 1 atm to 1 gram of SO2. Again, I'd like to remind you of the reference state. We have solid sulfur, solid pure sulfur, and pure oxygen in gas phase. We have them. Also at 25 Celsius degree, 1 atm. So for making SO2, you should have reaction at the reference state first. So that is the value was given to you. Delta H of reaction at 25 Celsius degree and 1 atm with extent of reaction. Plus then you should increase the temperature of 1 gram mole SO2 from 25 Celsius degree to unknown temperature. I have said we have reacted S plus O2 at 25 Celsius degree. So that is the 25 Celsius degree. So for the second step, you have the temperature difference with the heat capacity of SO2 gas phase with the molar flow rate for the upstream. So the H out SO2, this one, can be described by some value plus heat capacity with T minus 25. So with this one and the value this one, and you could neglect the first term on the right side of the equation. Therefore, we could calculate the temperature. This one, and then temperature is 7,500 Celsius degree. Here's the example 6.16, which is the last example of this chapter. 6. Synthesis of acetaldehyde. We want to design and build a reactor that produces 1200 kg/mol acetaldehyde CH3CHO per hour from ethanol and air. Two reactions are important at the reactor conditions. The first reactor, R1, produced our desired product, acetaldehyde, and while R3 produces an acetic acid as byproduct. This is the reaction we have in our reactors. Then here is the reactor. Ethyl alcohol, oxygen plus nitrogen, actually this is the air, is introduced into the reactor, and the reaction happens having R1 and R3, and the final product list is here. Ethyl alcohol as the unreacted reactant, and nitrogen, acetaldehyde, desired product, and acetic acid, the byproduct, and water, that is the product of the R1 reaction, and that's it. So we have all values about the component for each streams. Also, the extent of reaction was known, like the extent of reaction for R1 is 2000 kg/mol per hour, and the extent of reaction for R3 is 400 kg/mol per hour. And all reaction happens and proceeds at 300 Celsius degree and 1.5 atm. Question is, heat is required or heat should be extracted from the reaction? So we should calculate the Q term. Through the process, temperature constant, pressure constant, and phase is liquid constant. Only changeable thing is composition, which is induced by reactions. Then let me set up the energy balance equations. So no accumulation because this is the continuous reactor, and input minus output plus Q plus shaft work. Then in this case we could neglect the shaft work, so finally out minus in is equal to Q. The reactions actually occur at 300 Celsius degree over the whole process. So this problem looks very simple, but Appendix B has the formation data only as standard state. We should calculate the enthalpy term for output stream and input stream at 300 Celsius degree. However, what we have is the enthalpy data at 25 Celsius degree. Therefore, we construct an imaginary pathway. We have 5 steps for the pathway. The starting point is 1.5 atm and 300 Celsius degree. But the enthalpy values are known at 1.0 atm and 25 Celsius degree. So we should go to the reference point, where I mean the data point about the enthalpy value. Then we should go back. So step 1 is to decrease the pressure from 1.5 atm to 1.0 atm at 300 Celsius degree. In this case, no phase change. I mean, all over the whole process, we would keep the vapor phase. So step 1, still vapor phase without change in phase. And then I'd like to increase the temperature, decrease the temperature 300 Celsius degree to 25 Celsius degree. There is a step 2. And on this point, the reaction happens. I mean, enthalpy values are given at this state, 1 atm and 25 Celsius degree, and based on formation enthalpy energy, we could calculate the enthalpy difference or enthalpy change of reaction at this state. So we will make a reaction happen at this point, and then going back to the 300 Celsius degree at the constant pressure of 1.0 atm, and then you will increase the pressure to the original value, which is 1.5 atm. So we will have 5 steps to calculate the enthalpy term at 300 Celsius degree. Okay, then I'd like to calculate each term of energy balance equation. Enthalpy output minus enthalpy input is equal to Q. So finally, we will calculate the value of Q. Here is the scheme for the calculation pathway. So I will follow the calculation pathway. The step 1, we'll change the pressure from 1.5 atm to 1.0 atm. For ideal gas or low pressure vapors, there are no impact of the pressure on the enthalpy change. So we could neglect the first process. And then right now we are on the 1 atm and 300 Celsius degree. It's time to decrease the temperature from 300 to 25. So in that case, we could use the CP with temperature difference equations. So 25 minus 300 with the heat capacity. Then at the point 3, what happens? Reaction happens at 25 Celsius degree and 1 atm. So in this point, we'll try to calculate the enthalpy of reaction at the standard state. We have reaction 1 and reaction 3, and for each reaction we could calculate the enthalpy change by multiplying the specific the enthalpy of reaction with the extent of reaction for the corresponding reaction. So we have R1 plus R3. How to calculate the standard enthalpy of reaction? Of course, we could use the formation energy. For example, here is the standard enthalpy of R1 is equal to the sum of the formation energy of each species reactant or product at the standard state with the corresponding stoichiometric coefficient. So let me calculate the enthalpy of reaction 1. So minus 1 from the ethyl alcohol with its formation energy at the standard state, and then let's go to the second, the entity oxygen. So minus 0.5 stoichiometric coefficient, and its formation energy is 0 because O2 is the basic element in each neutral state. Now natural state plus 1 means acetaldehyde with its corresponding formation energy plus 1 for for H2O and its corresponding formation energy. Then we could calculate the standard state enthalpy of reaction 1. In the same way, you could calculate the enthalpy for the reaction 3. So, by summing those two enthalpy with the extent of reactions, we could calculate the enthalpy related to the reaction at the standard state. Again, I'd like to emphasize this point. Why we are going to 1.0 atm and 25 Celsius degree from 1.5 atm and 300 Celsius degree? Because we should use the standard state values like heat of combustion or formation enthalpy. Then we should go back to the original state. And the next step is for temperature increase. So 300 minus 25 Celsius degree. Then step 5, which can be neglected because pressure term can be neglected. Okay, so by using these equations, you could calculate the H out minus H in like that. Let me check the detail. So this first one is about this one, molar flow rate and the heat capacity with the temperature difference, or the other component in the input part. Something like that for the second step. And how about the third step? Those two things. And this is for output. In the output stream we have 1, 2, 3, 4 compounds there. And for the step 4, 300 minus 25, because we go from the 25 to 300. Then we could calculate the difference of enthalpy between input and output, which is estimated at minus 561,140 kilojoule per hour. So the value is about 560, this value for the heat. Minus means we will extract the heat from the system. So we should cool down the process. Here's the homework for chapter 6, and this is the very end of all class. That's it for the introduction to chemical process. Bye bye.